So, good morning to all, and welcome you all for the first online class on CMOS Analog IC design. Okay, lecture number 1 for online series. So, where we are, anyone? What we discussed? Okay, the last class. Actually, I started with amplifiers, right? We have been discussing unit 2, first half. So, let me call that is 2.1. It is amplifiers. So, can you take the syllabus overview page for this amplifiers? We want to start with first one is common source. Okay, then common, we discussed common gate, then we discussed common drain. Okay, or otherwise this is called drain follower, right? Drain follower, source follower, source follower. Okay, so these three topics actually we completed. What about the fourth topic? We are having two more topics, okay, in this 2.1. What about the fourth topic, anyone?
Cascode and differential.
So this one we completed, right? So let me, okay. The fourth one is another interesting topic. It is case code amplifier, not cascade. Okay. And the fifth one, then next interesting topic, it is differential amplifier. Okay. So let me start with the case code amplifier. So any doubt in single stage amplifier? Actually, these are all called single stage amplifiers. Single stage amplifiers. Okay, now this case code as well as this differential amplifier, it's coming under multi-stage. Already we studied these two keywords. One is called case code, another one is called cascade. So let me first put the heading case code amplifiers. Actually that is the heading, but straight away I don't want to jump into this case code amplifier. Before that, okay, I want to spend around 1 hour, okay, to speak about why case code. Why case code? Actually, it is quite interesting. Okay, we guess already we know what is the difference between cascade and case code. Anyone? Cascade, right? And case code. From my EC1 class, I think so. You can remember. உலகத்துல ஒரே ஒருத்தர் மட்டும்தான் கேஸ் கோடு யாரு in terms of PG you can say
Common base and common emitter.
yeah, common input stage is common emitter, output stage is common base. The ஒரே ஒரு configuration தான். Okay, the one and only possible or allowable, okay, configuration in case code, it is CE plus CB. What about cascade? That you can play with your own logic, right? You can go with either CE plus CE, or you can go with CE plus CC, or you can go with anything, right? Cascade and the case code, what's the difference? Anyone? Cascade and the case code, what is the difference? Anyone? Case code means one after another, or otherwise this is in horizontal direction. Actually, in multi-stage what is the meaning? And what is the drawback of single stage? Why we have moved to multi-stage? In general, multi-stage output of one stage, okay, is acting as the input of next stage. That is the meaning of multi-stage. In multi-stage, actually, we are having cascade and case code. Okay, so if you will connect horizontally, okay, then this is called cascade. We connect vertically, one above another. Okay, so either vertical or horizontal. Okay, so this is one after another, and this is one above another. So this and all actually we studied in PGT, okay, in from EC1. Now coming to the interesting part, case code, right? Why case code amplifier, and what are all the drawbacks of single stage amplifiers, namely this common source, common gate, common drain, and actually everywhere we are using most probably today's. Okay, you might have seen your op-amp internal circuit diagram. It may be based on PJT or based on MOS, whatever it may be. உள்ள internal structure பார்த்தீங்கன்னா you please just to Google it. Okay, internal யார் இருப்பாங்க, அந்த building blocks that we are going to study. Okay, the internal block diagram. Okay, it is not that much easy to understand the internal block diagram of op-amp. உள்ள யார் யார் இருப்பாங்கன்னா அவங்கள நம்ம படிச்சுட்டு இருக்கோம். ஃபர்ஸ்ட் டாபிக் உள்ள யார் இருப்பாங்கன்னா ஒரு கரண்ட் மிரர் இருப்பாங்க. அதுதான் உனக்கு யூனிட் 1ல ஃபர்ஸ்ட் செகண்ட் ஆஃப். ஃபர்ஸ்ட் ஃபண்டமெண்டல் படிச்சிட்டோம். அதுக்கப்புறம் ஒரு ஆப்பாம்ல உள்ள யார் இருப்பா, ஒரு கரண்ட் மிரர். ஓகே, ஸோ தி வெரி ஃபர்ஸ்ட் ஒன் ஆக்சுவலி கரண்ட் மிரர். அதனால தான் அது யூனிட் 1ல வச்சுருங்க, கரண்ட் மிரர். ஆம்பிளிஃபயர்ல இஃப் யூ வில் லுக் த இன்டர்னல் டயக்ராம் யூ கேன் சி கேஸ் கோட் ஆம்பிளிஃபயர் ஒன்லி, even not single stage amplifier. Then differential amplifier. So these are all the internal, the black diagram. If you will refer, you can find all these things. Okay, so we want to study separately. Okay, so that's the thing. So that's what first straight away if I will start with case code, then you won't be in a position to understand what is case code. That's what we studied single stage, like right, common source, common drain, and a common gate. So now, so here what is the allowable case code configuration? PJT it is CE plus CB. So here anyone ஏதாவது பேசுறா, இந்த தனுஷ் மாதிரி எனக்கு புலம்பு விட்டுறாரு. இன்ட்ராக்டிவ் இருக்குன்னு ஆசைப்படுறேன், இப்போ நடக்குமான்னு தெரியல. காமன் சோர்ஸ் பிளஸ் காமன் கேட். வெரி குட், தேங்க்யூ. ஸோ கேன் யூ ட்ரா? இந்த மாதிரி ஈஸியாக சொல்லி முடிச்சிடலாம், இதுதான் கேஸ் கோடு அப்படின்னு. பட் ஹவு அண்ட் ஒய் திஸ் காமன் சோர்ஸ் அண்ட் காமன் கேட் கேம், that I want to explain. Okay, so let me draw that case code amplifier. Okay, what is the unique property of this? Okay, so interview point of view it is very important. So can you sketch a very simple diagram, okay, for this case code amplifier, that CS common source plus common gate, right? So common source that take on NMOS. Here this is my VN. Common source, right? So source is grounded, and here you want to connect. This is my actually output, right? So output of first stage will act as input of next stage. Next stage that that is your common gate, right? So gate is grounded. Okay, who is the input of common gate? Who is the input of common gate? Source. Who is the source? Okay, so output of first stage, this is my output, okay, of stage 1 nu vechikkalama. Simply I am calling stage 1, or if you want you can write common source. And who is the input? So this is my input of stage 2, or simply this is my common gate, right? So the definition of cascade or case code. Output of one stage is acting as input of another stage, right? So this is my output of stage 1, it is acting as input of. Okay, so where you will get the output from stage 2. Stage 2 output is for a common gate. Okay, you want to connect this. Okay, this is my VDD. If you want you can connect RD. Okay, nothing wrong. And this is my Vout. Okay, RD. So stage 1. Okay, this is my common source. And stage 2. This is my common gate, right? Okay. So this is a general way, okay, to sketch a case code amplifier. Any difficulty in sketching this? But at this time, I want to. This is as per that guy Neiman. But as per Rasavi, it is quite interesting. Okay, I hope so. You will enjoy. Okay, Rasavi's flow this time. So let me start with. So before starting, case code amplifier. Okay, the case code configuration not only in amplifier, even we are having case code current source. Okay, so first of all, what is current source? Anyone? Let me start with ideal current source. What is the property of ideal current source? How will you test? Okay, the characteristics of ideal current source. Let me assume this is my current source, right? This is my current source having some current I out. Okay, how will you test this? Let me ask like this. I have given some device, some two-port network to you. Okay, you want to find whether the given two-port network is voltage source or current source. How will you test that? That's my question. Anyone? How will you test current source? Hereafter, for this lecture, CS means current source, not common stage. Okay, for each and every time I cannot write current source. So simply I will write C dot S, okay, not CS. CS now as per our notation, it is common stage, I mean common source. Here C dot S, this is for my convenience, okay, current source. So please keep it in mind. So how will you test that current source? It's quite interesting, right? For that, let me assume this is my current source. So what you will do? You want to apply some test signal, okay? Some, let me call this is some VA, and because of this, you will get some current IA. Now, if you sketch, okay, the curve VA versus IA, anyone, what you will get?
VA will be 0, sir.
You can vary, okay, VA from even minus infinity to plus infinite, nothing wrong. So what is the value for, assume I'm giving some 5 volt. If it is a current source, assume the current is some 100 amps, just assume. Okay, for 5 volt, what is the current? Since this is a current source, so this is called constant current source, right? So the name itself you can define. Constant current source means irrespective of the terminal voltage, right? Irrespective of the voltage, okay, irrespective of VA, the current is constant. So everywhere you will get a constant current with the value of I naught. Will you accept this? So this is the unique property of constant current source. So what about the slope? What about the slope? Anyone? You are
Zero.
getting flat current, so slope is 0. Okay. So what about the limit? What about this limit? What about the limit? It is infinite. Okay. You can vary this VA from minus infinite to plus infinite. Irrespective of this VA, this current, okay, should be constant. This is the way to test a current source. நம்ம கையில் ஒன்று கொடுத்துருக்குறாங்க, நமக்கு we don't know whether it is a current source or voltage source. Suppose நமக்கு ஒரு guess, okay, we can guess, okay, the current source தான் டெஸ்ட் பண்ணி பார்க்கலாம் அப்படின்னு நம்ம guess பண்றோம். Okay, just we are guessing, and I want to know whether it is acting as a current source or not. For that, what you want to do? Just take a voltage source and connect, okay, across it, vary the voltage, and if you measure the current, and if you will get a constant current, then you can conclude the given device, the given network, or the given two terminal, it is a current source. So this is the way to test a constant current source. Okay, so the property current is constant, current is constant, okay, and independent of voltage across it. So this is the property, right, of a, any doubt in this? Current is constant and independent of voltage across it. This is the ideal current source, property of ideal current source. Similarly, can you build the same concept for voltage source? How will you test a voltage source? I will leave this question, okay, up to you. Please find the testing method, okay, to find the voltage source that you can build. But now I am in need of this current source. So any difficulty? So far so good?
Sir.
Okay. So I'm asking you, okay, to buy a current source, and just assume you went to shop, okay, and you are asking the shopkeeper for a current source. Will you get a current source? Will he or she give a current source to you? What you will do? Suppose if I am asking you to purchase a current source, so what you will do? This is ideal current source, but we know in the in the real world, okay, we don't have ideal current source. So how will you build, okay, a current source? For that, I want to give you three important observations, and I hope so you will enjoy all these observations. Observation number one: let's build a source, right? Let's build a current source. This topic already we discussed, but anyhow, I want to repeat. Okay. Who will acting as a current source? Observation one. Please put the heading. Let's build a current source. Who will acting as a current source? Anyone? No, first unit, first. Who is acting as a current source? Yeah, passing.
MOSFET, sir.
MOSFET. Okay. Where? In which region?
Saturation.
Okay. So MOSFET, we know that. Okay. We know that MOSFET in saturation region. Okay. Will act as a current source. Okay. So நமக்கு தெரியும். This is my take on NMOS. NMOS, right? You take this two terminal device, and here it should be connected to ground, right? And here you want to give this VGS biasing voltage. Let me call this is biasing voltage VB. Actually, this is VGS, right? Okay. And here you will get some current ID. Okay, and assume it is in saturation. What is the condition for saturation? What's the condition for saturation? This voltage, right? It is VDS plus minus. VDS. Any difficulty in network, or are you facing any audio or video problem? நீ பேசுற எதுவுமே எனக்கு கிளியரா கேட்கல இது வரைக்கும். என்னோட வாய்ஸ் எப்படி இருக்கு? நீங்க பேசுற எல்லாரும் என்ன சொல்ல வந்தாலும் கிளியரா இல்லை எனக்கு ஸ்டக் ஆகுது. ஐ டோன்ட் நோ வெதர் நெட்வொர்க் ப்ராப்ளம் உனக்கா எனக்கு. என்னோட கொஸ்டின் நான் பேசுறது கிளியரா கேக்குதா?
எஸ் சார் கேக்குது சார்.
Okay ma. So you know the condition for saturation, VDS is greater than, okay, or equal to VGS minus the threshold voltage, right? Okay. Can you sketch this IV characteristics? Okay. This is actually this voltage VDS versus this current ID. Okay. This already we derived. Okay. எப்படி இருக்கும்? Will you get a constant current? Actually, even in saturation, current எப்படி இருக்கும்? Because of the slope, it won't be zero. Okay, this is still saturation region. So till here my value, it is VGS minus VTH, or otherwise as per this notation is the biasing voltage minus VTH. Okay, of below VGS minus VTH curve எப்படிமா இருக்கும்? So this is no longer a current source, right? no longer a current source in linear region. Please make a note, it's very important. So in saturation region alone, okay, in saturation region alone, it is acting as a current source. Is it a constant current source? No, because ideally எப்படி இருக்கணும், we are expecting, okay, this is the ideal one, but this is practical one. Okay, and you know we are having two type of current source, NMOS current source and PMOS current source. So what is the property of NMOS current source? NMOS, anyone? NMOS current source enna பண்ணனும்?
From node
Node
to
to ground.
ground only.
So node to ground. Okay, this is my NMOS. What about PMOS? VDD, right? Power supply VDD to node, right? This is my PMOS. So based on the application, so based on the requirement, either you can go with NMOS or PMOS, that you know. But what is the drawback here? What's the drawback here? In this, we are having two major drawbacks. Disadvantage. Point number one, is it a constant current source? Is it a constant current source?
No, sir.
So output current is not constant, right? Even in saturation region, it's not constant. Constant even in saturation region. That is the very first drawback. Actually, we are expecting constant current source, and you know the property of constant current source, slopes would be zero, right? You want to get a flat response like this. இந்த மாதிரி இருக்கணும். Okay, but நமக்கு எப்படி இருக்கு? We are getting a, you know, because of channel length modulation, that story, you know, current increases when you are increasing this VDS. Okay, so output current is not constant, okay, even in saturation region. That's the very first drawback. Second drawback, it's another drawback, it's quite interesting. What about the limit here? What about the lower limit? What about the lower limit in this? Is there any lower limit?
VGS minus VTH.
No, I am asking about this constant current source, ideal constant current source.
Minus
In
infinity.
ideal, minus infinite. So there is no lower limit, right? You can vary if you want. You can go to minus 100, or if you want, you can go to minus 1000. Okay, minus 2000. There is no lower limit. But what about here? Here, what is the lower limit? Is it minus infinite? What about the lower limit? Lower limit, you can go up to VGS minus VTH, right? So the voltage range is limited. The voltage range is limited. Okay, actually, this bracket since lower limit is bounded by, since the lower limit is, you know, VGS minus VTH. Okay, let me erase this. So this is point number 2. So two major drawbacks as per Rasavi. Okay, I hope so it is easy to remember all the 2 points, and it is quite interesting also, right? So enga start pannom or constant current source. I want to give 3 observation. Observation 1 already we know, another, that is the practical current source, that we know how to build, okay, a practical current source either by using NMOS or PMOS. But what's a drawback in practical current source? If you use NMOS or PMOS, very first drawback, the current is not constant even in saturation region. Actually, what we are telling, in saturation region, NMOS or PMOS is acting as a current source. But what is the condition? If lambda equal to 0, correct? Here lambda is actually greater than 0. If lambda equal to 0, then you will get ideal response. But it is not possible practically. So we want to play with the lambda greater than 0. Greater than 0 means that because of channel length modulation, output current increases, nothing but slope increases, correct? Okay. So that's the first observation, first drawback. Second drawback, the limit is bounded, right? The lower limit, it is VGS minus VTH, not like ideal current source. So any difficulty in observation 1? So observation 2, now my question, how to improve the current source? What we discussed in observation number 1, actually we are expecting constant current even in saturation region, but slope increases. So my question, how to improve the current source? Anyone? Is there any idea? Actually slope increases, right? So I want to decrease the slope, right? Decrease the slope. Okay. So far so good. Any doubt? So to improve current source means you want to decrease the slope, correct? What is the slope here? This is my VDS. This is my ID. Okay. And in saturation, actually. So what is the slope here? Anyone? Slope. What is the quantity? What is the name? Slope, change in
Dou ID
y-axis.
by dou VDS.
Okay. So dou ID divided by dou VDS. So what is the name for this? What is ID versus VDS? That is trans conductance, right? Or resistance? Is it conductance or resistance?
Conductance.
So conductance. It has to be increased or decreased. Conductance.
Increase.
Conductance has to be decreased. Then what about resistance? As per our notation, this is called output, right? So output conductance, not trans conductance, because we are playing VDS versus ID. Both are at output side. So output conductance actually has to be decreased. So what about output resistance? Output resistance has to be increased. So here is the point. How to improve the current source means you want to by improving, okay, or otherwise let me write like this, by increasing, simply I am writing by increasing RO. That is the keyword here. The point for take any two-port network. If you will increase the output resistance, then it will act as a constant current source. Okay, because by increasing resistance, actually we are decreasing conductance. Actually, we are decreasing slope, right? So by decreasing, you can achieve. Okay, so actually this is in saturation. Okay, so this is my idea. So how to achieve this? By increasing output resistance. So this is the expected keyword. Please make a note. Okay, so how to improve the current source? Okay, so here we discussed two things. What's the very first drawback? Even output current is not constant. Okay, so which means slope increases, right? Slope increases. So I want to decrease the slope. Decreasing the slope means increasing the output resistance. Any doubt in this point? Any doubts so far?
No, sir.
Okay. So here I am having some MOSFET, right? Let me try that MOSFET. Some MOS. Okay. And here you are giving some biasing voltage. And here you are measuring this ID. Okay. But you know, the current is not a constant one, even in saturation region. So I want to improve the current source. Nothing but I want to increase the output resistance. Now my question: how to increase, or we discussed five, okay, different variants, right? Five variants in common source stage, CS stage. Out of five, who is giving high input resistance? Sorry, high output resistance. 5 வேரியன்ட் படிச்சேன். 5 வேரியன்ட்ல யாருக்கு வந்துட்டு அவுட்புட் ரெசிஸ்டன்ஸ் அதிகமா இருக்கும்? It's quite interesting. We derived all the 5 variants output resistance. Now வருங்க. Anyone? ஒரு 5 வேரியன்ட் பார்த்தோம். At least can you name all the 5 variants? Anyone? பாலதீபி இருக்கியாமா? நேம் சொல்லி கூப்பிடலாம். 13 பேர் தானே. We will play. பாலதீபிகா are you there? கம்யூனிஸ்ட் போயிட்டியா? யார் இருக்கா? கூகுள் வாய்ஸ் கேட்டேன், கார்த்திக் வாய்ஸ் கேட்டேன், கேட்காத வாய்ஸ். ஸ்ரீலிந்தா.
Sir,
Name the 5 variants of CS.
sir, resistive load,
Break
sir, common source stage, and
Resistive load, அதுக்கப்புறம் second one,
common source stage with constant current source, sir.
constant current source. Third one,
With diode connected device, sir.
diode connected to this. Fourth one, active load. Fifth one,
Source
RS,
degeneration.
source degeneration. Okay. Out
Yes.
of 5, இந்த 5ல யாருக்கு வந்து அவுட்புட் ரெசிஸ்டன்ஸ் அதிகம்? 5 பேர் எடு. 5 பேர் எடுத்து கம்பேர் பண்ணி பாரு. யாருக்கு அதிகம்? Anyone got the point? If you know the answer, you please unmute and let me know. நம்ம we derived.
சார் சோர்ஸ் ஃபாலோவர் நம்ம எடுத்துக்கலாம் சார்.
Source follower. Here I am speaking about current source, right? Current source na idan
Source
enakku current
degeneration.
yeah.
The source degeneration output resistance adhigam sir.
Pogula. Correct ma. Thank you ma. So before that, Karthikeyan, one of the question answer is that I am speaking about current source. This is my current source. Is it source follower? So it is common source, right? Because we are giving some input, okay? The
Yes, sir.
gate, and we are getting the output, okay, at drain. இதana பண்ணிக்கிட்டு இருக்கோம் நம்ம.
Yes, sir.
So this is a common source, okay. And as Kogul told, very good. அந்த 5 பேர்ல யாருக்கு வந்துட்டு how to increase RO அப்படின்னா by connecting RS. The point புரிஞ்சுக்க முடியுதா? This is nothing but common source stage with source degeneration, correct? The one what we discussed in common source stage. Okay, so let me connect one RS. Okay, first, before RS, without RS, what is the output resistance here? Anyone? R out formula without RS. What is this? Common source stage. Okay, and assume here you are having some VDD. Okay, and this is open means actually here you are having constant current source. In that way you want to imagine. This is my ID, correct? So common source stage with constant current source as load. What is the output resistance? If we will derive, we will get, I believe, R out. Okay, assume lambda not lambda greater than 0. So R out parallel with, what about this guy? What is the internal resistance of current source? It is infinite. So you will get R out. Or suppose if we will connect RD, if RD is the first variant common source stage with the resistive load, at that time R out equal to small R out parallel with RD. Okay, and you know what is the output resistance of the third one, diode connected device, fourth one active load. Now coming to the fifth one. Suppose if we will connect, okay, let me copy this here and paste. Yeah. Now take the same common source stage. This time I want to increase the output resistance. So as I told, just connect one or two. Okay. So now what is the output resistance? Anyone? If I have given one formula, we verbalize this. What was the statement? Output resistance of common source stage with source stage generation. We verbalized it. What is the formula? How to write the formula? Anyone? And this is not RT, this is RS.
Sir,
Yeah.
internal impedance of MOSFET.
That is called intrinsic gain, not internal impedance. You are good, okay, but try to change the statement. It is intrinsic gain, correct?
Yes. Okay, yes, sir.
Intrinsic gain. What is intrinsic gain? Nothing but GM, right? Times RO. That is the intrinsic gain. So how to write? Please, it is 1 plus that intrinsic gain. This GM RO times this
Source
resistance RS plus you want to add this RO. Okay. If no RS, okay. If RS equal to 0, then what is your R out? It is simply RO, small RO, correct? It is simply small RO. So is it making sense? Yeah, right? So we know if R is equal to 0, already we derived this output resistance RO, small RO. If we will include RS, then this formula already we derived, okay? And we verbalized this too. This 1 plus GM times GM RO times RS plus RO. Okay. So yeah, what about this gain? It is approximately, okay. Now this GM RO, it is very, very greater than 1. Then what about this approximation? 1 plus GM RO times becomes GM RO times RS, okay, plus small RO. Now this GM RORS is very, very greater than small RO. Therefore, what is your RO? Once again, it is almost equal to GM RO times RS. So, initially, what was our output resistance? It is RO. Okay. So now output resistance, it is multiplied. This RO is multiplied by GMRS, right? Obviously, therefore R out is high. If R out is high, what is the conclusion? So conclusion. So what we expected, we are expecting a constant current source. This is my VDS. This is my ID. But even in saturation, actually slope increases, right? Till this is VGS minus VTH. Okay, this is my linear triode region. But actually, what we are expecting, constant current source. This is, can I write this time, if R is equal to 0, the slope actually increases. Now by adding RS greater than 0, slope decrease. Okay, because output resistance increases, so slope decreases. So we are moving towards constant current source. Okay, so that is the logic. Okay, so is it a good way to approach way to get a constant current source? So first ஒன்று படித்தோம் constant current source. அதனால் என்னன்னு படித்தோம். அப்சர்வேஷன் உள்ள என்ன சொல்லி கொடுத்தேன், ஃப்ளோ எப்படி இருந்துச்சு. நம்ம ஒரு NMOS யூஸ் பண்றோம் அப்படின்னா இட் இஸ் நாட் a constant current source. அப்போ அதை எப்படி அதில் டிராபேக் படித்தோம், அதை ஓவர் கம் பண்றதுக்காக எங்க வந்தோம், காமன் சோர்ஸ் வித் சோர்ஸ் ரீஜெனரேஷன். ஓகே, ஸோ ஹவு டு இம்ப்ரூவ் த கரண்ட் சோர்ஸ் அப்படின்னா சிம்பிள் வேர்ட்ஸ் பை கனெக்டிங் RS or otherwise by increasing output resistance. How to increase output resistance, that we know by connecting RS. Okay, RS connect பண்ணியாச்சு. Somehow we are moving towards constant current source, but this time what is the drawback here? Anyone? Inga okay, constant, we are moving towards constant current even in saturation region. That's the advantage, right? So let me write first. Advantage, okay, high output resistance. High output resistance, that is the indication of constant current source. But what is the drawback? Anyone? But with this I will complete today's session. Okay. That is simple, right? Here we connected this
GM is
biasing volt. Sorry, ma?
GM, so that PVT.
GM, PVT. One way you are thinking, talking about GM, because GM depends on process variable temperature. Okay, but in another way you want to think, let me explain that drawback. Okay, so please listen me carefully. So this is my okay, this is my actually gate to source voltage, right? Plus minus, and this is my yes, right? What about this current? Because this current is ID, this current also ID, correct? So now can you apply KVL at input loop? Apply KVL at input loop. Applied voltage, actually this biasing voltage VB, it equals, okay, first between gate to source VGS, then the voltage drop across source, it is VG ID RS, right? So this voltage VB, this voltage is addition of these two voltages, as per KVL. Okay. Now what happened, okay, to the lower limit? What happens to lower limit? Anyone? Previously the lower limit, it is VGS minus VTH, one threshold, right? VGS minus one threshold. Now what is the limit? Anyone? Because of connecting this RS, now what is the limit? What happens to lower limit? Anyone? Now this is nothing but actually VB, correct? VB minus VTH. Now VB becomes VGS plus IDRS. Okay, so minus VTH. Can you understand? By connecting RS here, because of this RS, the voltage drop across RS is added with this VGS, correct? So lower limit increases or decreases?
Increases.
Increases, moving towards left or right?
Right.
So lower limit moving towards right. Therefore, okay, so what is the range? The output, I mean the range is limited, right? Therefore range is limited. Which range? That lower limit range. Okay, so just there is no RS, assume this is my limit, it is VGS minus VTH. Okay, now by connecting RS, Okay, actually it is VGS plus IDRS time. The voltage across RS is ordered minus VTH. Suppose if this is some 1.2 volt, assume. Okay, the voltage drop across RS is some 0.6. Now, what is the limit here? Anyone? Assume this VGS minus VTH is 1.2 volt. And assume this voltage drop across RS is 0.6 volt. So the limit is this time 1.2 plus 0.6, 1.8 volt. So the limit is, the range is limited, correct? So here the range எப்படி இருந்திருக்கும் இங்க இருந்து இங்க வரைக்கும் இருந்திருக்கும். Okay, but this time, so lower limit இங்க எனக்கு என்ன இருந்துச்சு? Lower limit is 1.2. So here lower limit, just for our understanding purpose, okay, to illustrate, I have taken some numerical 1.8. So what is the drawback? More limited range. So conclusion, drawback, more limited range. How to improve this? You please think about this. Okay, so that's it for today's class. So any doubt? So எங்க ஆரம்பிச்சேன், ஒரு கான்ஸ்டன்ட் கரண்ட் சோர்ஸ், அதோட ப்ராப்பர்ட்டி படிச்சோம். அப்புறம் I want to give 3 observations, ரெண்டு தான் கொடுத்துருக்கேன். ஃபர்ஸ்ட் அப்சர்வேஷன் என்ன? லெட்ஸ் பில்ட் a கரண்ட் சோர்ஸ். அதனுடைய லிமிட்டேஷன் பார்த்தோம். ரெண்டு லிமிட்டேஷன். கரண்ட் சோர்ஸ் கான்ஸ்டன்ட் கரண்ட் சோர்ஸா இல்ல. ஈவன் இன் சேச்சுரேஷன் ரீஜன் ஆக்சுவலி கரண்ட் என்ன ஆச்சு எனக்கு? இன்க்ரீசஸ். ரெண்டாவது டிராபேக் லிமிட்டட் ரேஞ்ச், லோயர் லிமிட்டட் ரேஞ்ச். லோயர் ரேஞ்ச் இஸ் லிமிட்டட். ரெண்டு டிராபேக். அதை எப்படி ஓவர் கம் பண்றது அப்படின்னு சொல்லிட்டு ரெண்டாவது அப்சர்வேஷன் என்ன ஹெட்டிங் போட்டேன்? ஹவு டு இம்ப்ரூவ் தி கரண்ட் சோர்ஸ் அப்படின்ட்டு. அது ஹவு டு இம்ப்ரூவ் அப்படின்னா பை இன்க்ரீசிங் அவுட்புட் ரெசிஸ்டன்ஸ். ஹவு டு இன்க்ரீஸ் அவுட்புட் ரெசிஸ்டன்ஸ் அப்படின்னா பை கனெக்டிங் ஆர்எஸ். யா, ஒரு கண்டிஷன் சாட்டிஸ்ஃபை ஆச்சு. கரண்ட் வந்து கான்ஸ்டன்டா போச்சு. கரண்ட் மூவ்ஸ் டுவர்ட்ஸ் கான்ஸ்டன்ட் கரண்ட். பட் டிராபேக் என்னாச்சு? ரேஞ்ச். அது அகைன் என்ன ஆகுது? எனக்கு லிமிட் ஆகுது. Okay, more limited range. So how to improve this? So that is the third observation it is speaking about. That is the expected one, case code current source. Okay, so we will pick up it. Okay, we'll pick this concept, okay, for tomorrow's class, and I will summarize the first two observations and I will give the conclusion. Then why case code? Then at the time we will how to impose this. This is the keyword, by case code current source. How? Please think about this. Okay, we will pick up this constant for tomorrow's class and we will study about constant current source. Then I will jump into the topic called case code amplifier. Okay, so before studying case code amplifier, you want to study case code current source. Then it is easy to understand. Okay, so any doubt?
No, sir.
Those who are having doubts, you may stay. Others, okay, you may leave. Let me stop the recording. So, thank you. Thanks for your attention. Thank you.